right, welcome to 26-4. Here we'll talk about the glomerulus primarily and how we regulate the glomerulus in order to produce filtrate. So as we know, the heart is pushing blood all the time throughout the veins and arteries, and this pressure on the vessels is what we call hydrostatic pressure. And this hydrostatic pressure, as we learned from the blood chapter, is also what promotes filtration. And so remember, we need hydrostatic pressure to be greater than the interstitial pressure and the interstitial osmotic pressure, interstitial colloid pressure in order to promote filtration. So that'll come into play here a lot. Let's talk about glomerular filtration. So the first thing that we need to understand is how the glomerulus is even structurally made. I'm not going to draw too many pictures here. So on the right-hand side, I brought us back to one of the images that we drew out, which is the juxtaglomerular complex right next to the glomerular capsule. And so if you remember the glomerulus, we drew some blue dots as podocytes, but we can actually zoom in a little bit further and see how these podocytes are doing what they're supposed to do. So the glomerulus is a capillary, but it's a fenestrated capillary, and that means it has spaces, and those spaces are going to allow small solutes to pass. Then just superficial to that capillary is basement membrane, and that basement membrane is only going to allow some plasma proteins, really small ones, really small ones, nutrients and ions to pass through. Okay, that's great. But our final step that actually allows the final materials to pass are the podocytes. And the podocytes are the ones that can actually contract or relax, changing the diameter of those filtration slits to allow whatever it is passed. So the podocytes are only going to allow really small items to pass through. Notice we do not have any red blood cells passing through. If we did, that would be super bad news bears. That means something is really wrong with your nephron. So no red blood cells are passing through. No really big molecules are passing through. Just like we said in the previous video, only really small ions, acids, sugars, only things like that are actually being able to pass through. Okay, so let's name some things about how we regulate this process. So we have something called GFR. GFR is commonly used in the clinic as well, so you might hear this. But GFR is glomerular filtration rate. You're more than welcome to abbreviate it as GFR on your exam, but you need to understand what GFR stands for. So I would recommend calling it glomerular filtration rate until you actually become comfortable with what that means. So what is it? This is essentially the hydrostatic pressure, including colloid osmotic pressure of the blood within the glomerulus. So whatever volume of liquid is trying to leave the glomerulus is this GFR. And we have to talk about the efferent arteriole versus the afferent arteriole. So afferent is coming in, A for arrive, E for exit. And what's actually really interesting is the efferent arteriole is slightly narrower than the afferent arteriole. And this is really important because we want to keep as much blood in the glomerulus as possible in order to produce the most amount of filtrate as possible, or at least the most efficient amount of filtrate as possible. And so if we have a lot of blood coming in for whatever reason, we might not have enough time for that blood to actually get filtered out by the podocytes in the basement membrane and the fenestrated capillary. So we actually want the efferent arteriole to be a little bit more restricted in order to help push some of that blood back into the glomerulus in order to really make sure that we filtered it out. So at any given time, efferent arteriole is always going to be a little bit more narrow than the afferent arteriole. Now there are some mechanisms where we can change the diameter of the efferent and the afferent, but we mainly only talk about changing the diameter of the afferent arteriole because efferent arteriole is pretty static in what it's doing. Okay. Then we have something called capsular hydrostatic pressure. This is basically what is in the capsular space that is opposing the GFR from the glomerulus. So we want to promote filtration, so we need GFR to be bigger than this pressure in order to actually move things out of the glomerulus into the capsular space. And here NHP is showing up again as net hydrostatic pressure. So here we can subtract capsular hydrostatic pressure from glomerular filtration pressure or glomerular hydrostatic pressure, either way. If this is a positive value, we would be promoting filtration. If this was a negative value, we would be promoting absorption. There should never be a negative value. If it's a negative value, that's renal failure, and then that's, bad news bears. It should never be a negative value, not even in the short term. It should not be a negative value. It might be 0, but it should never be negative. That's really bad news, bears. Here's a summary picture that your book gives you, going through the different pressures. We don't expect you to know the numbers in this course, but what we do need you to know is positive is filtration, negative is absorption. And this picture does a really good job of showing you where those ions are as part of the filtrate. And it does a good job summarizing what's going on. But essentially, you need a higher GFP against all the other pressures that are in the capsular space in order to promote filtration. Okay, so what things oppose filtration? BCOP, so blood colloid osmotic pressure. So this is all of the ions and solutes in the capsular space. If there's too much there, that could oppose filtration by pulling more water out of the glomerulus versus actually pulling out filtrate out of the glomerulus. Water's great and all, but really at the end of the day, we're going to reabsorb all that water anyway, so there's no point in really pulling it out of the glomerulus. So this opposes GFP. Again, if we have a net filtration pressure and we have a net hydrostatic pressure minus blood colloid osmotic pressure, if this is positive value, we're filtrating. If it's a negative value, we're absorbing. So the rate of GFR, we mentioned this on a previous slide with the fish tank, but this rate, this is where we get those numbers from. This is something that's relatively easy to calculate, but the number that we care about is 125 mils per minute. This is about 10% of the fluid that actually arrives to the kidneys gets made into filtrate, so actually gets filtered out of the glomerulus. We make about 180 liters of this a day, which is absolutely crazy. And then about 70 times, that equals about 70 times of the total plasma volume in the human body, which is absolutely amazing. And this is a very regulated environment because we're dealing with so much fluid, we're dealing with filtering out the blood. This is a really, really important structure in the body. So we can be affected by blood pressure, but for the most part, we really don't like to be affected by blood pressure. We want to maintain consistency as much as possible in the nephron because really at the end of the day, the tube doesn't have a lot of wiggle room in its capabilities. The glomerulus has some wiggle room, the afferent arteriole has some wiggle room, the juxtaglomerulus complex has some wiggle room. We can do things with aldosterone and ADH and PTH at the end, but other than that, we can't really manipulate the tube very well. So the glomerulus is kind of that one-stop shop for making sure that whatever filtrate comes through is something that we can actually clean up before it becomes urine. So this is something that really needs to be as consistently. It has to have the same amount of blood coming in at all times, ideally, because that's all that it can withstand. All right, so let's talk about how we regulate this. We'll do 3 different chunks, so autoregulation, hormonal, and autonomic. So starting with autoregulation, so this is meaning self-regulation. We have myogenic mechanisms. So we can change the pressure in the actual arterioles. So like I mentioned, we could change the efferent arteriole, but if we were going to change it, we would probably increase the constriction. And increasing the constriction would hopefully increase the amount of blood pressure that enters into the glomerulus so that we can promote filtration. You could change the constriction of the afferent arteriole, but the only reason you would ever do this is because, let's say you're working out, the rest of your body is going to need the skeletal muscle is going to need a lot of that blood anyway, so that blood gets shunted there, not as much goes to the kidneys. And in a response, the glomerulus still wants the same GFR. So in order to do that, it will squeeze off the afferent arteriole so that we increase the amount of blood that's the amount of pressure that's coming from the afferent arteriole to promote more pressure in the glomerulus so that we can continue the same amount of filtrate production. This is why it's really important to drink water while you exercise, is so that you can continue to have enough blood volume in order for some of it to still get to the kidneys. But other than that, we don't really like to mess with the afferent arteriole unless we absolutely have to. So if systemic blood pressure increases, so we're thinking blood pressure everywhere, the kidneys, again, don't want to handle that extra amount of blood pressure because that's they won't filter better if more blood is coming in. They can only filter as good as what it's designed for, so it can only filter ideally 125 mils a minute. So if there was more blood in there, we might miss some of those ions that need to be part of the filtrate, and that's not a good thing. So in order to offset that high systemic blood pressure, the afferent arteriole will stretch in order to increase the diameter so that we can hopefully maintain and equilibrate the amount of blood that's actually coming into the glomerulus. All right, hormonal regulation. So we know how renin works going through the RAS system, but renin is going to be released in response to low blood pressure. It's stimulated, or we can stimulate the juxtaglomerular cells by sympathetics. That can also release renin. Or we can decrease the amount of water that's actually in the tubular fluid. So by the time it comes back on itself at the macula densa could say, oh my gosh, we don't have enough water over here. We need to increase blood pressure so that we have enough water pumping through, so hopefully increasing venous return. And that could eventually, and that system could be turned on by renin, so we would release renin as a result. ANP. ANP is the only hormone that is going to work against aldosterone at the distal convoluted tubule and the collecting duct, but mainly the distal convoluted tubule, in order to decrease sodium reabsorption, in order to decrease blood pressure. Remember, we talked about ANP in the heart and how it gets released in response to the baroreceptors if it sees too much stretch. But it also works against, it's an antagonist to aldosterone, so that we don't hold on to as much sodium, thus we don't hold on to as much water. So ideally, venous return decreases, so cardiac output decreases. Last but not least, autonomics. So it's mainly sympathetics. Sympathetics are going to vasoconstrict as they normally do. Like I said, they're not going to really affect the efferents. We're only going to really play around with the afferents. And the point is to maintain GFR. So if blood is coming in too fast or too much, afferent arterioles are going to decrease so that we can slow it down, so that we can maintain that GFR, that ideal GFR. If we, for whatever reason, are exercising too much and the glomerulus doesn't have enough, not the glomerulus, but the kidney tissue doesn't have enough O2 in order to supply it, we could also start breaking down proteins, which eventually would end up in the urine, and then that could lead to proteinuria, oh my goodness, due to low oxygen levels. So this is really like, this would not really happen to your regular athlete. We're talking like professional athletes who are exercising more than that is healthy to them. This really doesn't happen too much in the population, but it potentially could.